I believe we are live now. Yes. All right.
Great.
Okay, so we are live here. We are live. All right. 3, 2, 1. Welcome, everyone. Very happy to be here. I would like to welcome everyone to the second lecture in our guest lecture series for the course GSD-6338 Introduction to Computational Design that is taught yearly at the Harvard Graduate School of Design. It is my honor and my pleasure to welcome Gabriella Rossi from CITA to this lecture. I met her not so long ago in a digital event, actually, thanks
virtually,
to COVID.
yes.
Virtually, these things that happen with COVID. And I was personally very impressed by her work. And that's what inspired me to bring her over here today. Just a couple, before I introduce Gabriella and we go into the lecture, a couple of logistical notes. This lecture is happening virtually on Zoom, and everyone from the Harvard and GSD community was invited to join the Zoom call live. However, this lecture is also being live streamed to YouTube. And so there is a community, there's a large community of people who are watching this live also from YouTube. And I will be more than happy to welcome everyone, whether if you are on the Zoom call or on YouTube, to participate. So what we're going to do is that Gabriella is going to give her lecture. And then after that, I will open it to Q&A from people in this call, on the Zoom call. And then after that, those who might be posting questions or comments or any other things on the chat on the YouTube video, I will relay some of those questions to Gabriella, and that will be a way for her to respond and to address those questions. Okay. And with that, I think we can just get started. So I would like to welcome again Gabriella, who's currently a PhD student, PhD fellow at CITA in part of the Royal Danish Academy in Denmark, in Copenhagen, correct?
Correct.
Yes. So her research, as she will probably talk about, focuses mostly on machine learning technologies applied to robotic fabrication, what we may call informed fabrication, or maybe she's going to offer some more interesting terms for us to unpack. She's been doing a lot of work on this as part of her PhD research and previously as her work as research assistant, also at CITA, where she also teaches at the Masters of Computation in Architecture, and where she has also guest taught in several institutions such as the University of Technology in Sydney and the Southeast University in Nanjing in China, right?
Correct.
She holds a Bachelor of Science cum laude from the Politecnico di Milano and a Master's of Arts also from the Royal Academy of Arts. And before that, she has occupied several computational design specialist roles, such as, for example, Odico, which I believe is a company in Denmark that does robotic fabrication.
Exactly.
I've seen a lot of their work out there. It's very, very interesting. And he's also a member of the Danish Association of Architects. Without further ado, I'm going to welcome her in, and I'm going to invite you to share your screen, and then I'm going to shut up.
Yes, thank you, Jose Luis, for the very kind introduction, and I hope you all see the right side of my slides.
We
do. Great, yes. Fantastic. So it's really an honor and a great pleasure to be here, even so virtually in this weird sort of hybrid post-pandemic world that we live in, where people can just Zoom into meetings while sitting on their desk at midnight somewhere else around the world. And I've titled this lecture Machine Learning and Datasets for Architectural Robotic Fabrication. But before I dive into that, I would like to take a few minutes just to introduce the context of the work that I'll be presenting to you. Based in Copenhagen, Denmark, as Jose Luis mentioned, at the Royal Danish Academy, and this is how it looks on a sunny day, which have become quite rare this time of the year. And I am part of CITA, which is the Center for Information Technology and Architecture, which is a ground research center. So in contrast maybe to Andrew Human's lecture last week, I will be providing mostly an academic perspective rather than an industry perspective on computational design and architectural informatics, or whatever one should call this interdisciplinary thing that we do. And this also means that I might be providing you with more provocations and questions than I will provide you with answers during this talk, and I hope that's okay. And so at CITA, we look into the relationship between digital technologies and architecture and how technology affects space, but also how digital practice impacts architectural design thinking. And we do that by programming, of course, but also by designing and building demonstrators and full-scale prototypes. And a lot of our research is integrated with our 2-year specialized master program, Computation in Architecture, where students actually engage actively with ongoing research projects at CITA. And I think it's really important to underline when you work in academia that you are never doing research on your own, but you're always part of a group, and that you are actually always standing on the shoulders of giants, whether those giants come from your own institutions or are peers and scholars in the field. You never work alone, and you always build on top of other previous research that has been created before you. And this is particularly true, being based at CITA, which has been founded in 2005 by Professor Mette Ramsgaard-Thomsen, and has across the years had several theoretical frameworks that were guiding the investigative work that has been produced. And I think for me, it's always fascinating to look back at the history of a research group and try to understand how did we get there and what did we learn along the way. So right now, and for the upcoming couple of years at CITA, we're looking at eco-metabolistic architecture, so how to understand new materials, biomaterials, cellulose, which is what I'm actually focusing on as a topic for my PhD, but also fungi, bacteria, and how to instrumentalize biodesign and how to think of time and architecture in a different way. So most importantly, how is it that we can model differently by taking time and the dynamics of life cycles into considerations for these new materials? But a lot of the ideas that enable us to get to this, start of a new project actually come from the project before, so from the complex modeling project, which we've actually wrapped up a lot of the findings in a monograph, which you can probably see. If you use the QR code here, you can have a an openly accessible PDF to the monograph, which I invite you to skim through. But I will refer particularly to this chapter here, which is about information-rich design. So it is really the realization that our digital and computational workflow and design practice has led to data, and so much data that is being produced, data that is multiscalar, data that is relational, data that is both about geometry, but also about performance and material behavior. And our models have megabytes and megabytes of this data that is, kind of unleashed, it can be unleashed potential. So this is a very different setting from, say, mid-70s. So, for example, this paper by Alexandra Marmot and John Giro, where they set up to produce an empirical model of elevator lobbies in skyscrapers in New York, if I'm not mistaken. And so they had to manually survey 67 building lobbies, extract parameters, build a corpus, and then produce a statistical model. So somehow what we're doing today is the same exercise that they've been doing 50 years ago, just we do it in a more digitally empowered way. And so data is actually machine learning's first principle. It's the most important component of any machine learning problem. Then the reason we can seriously think about machine learning as a modeling paradigm in a lot of disciplines is because we have enough, if not too much, data right now. So that's point number one. Hold on to that idea because there is kind of a small asterisk that we will get back to in a bit. But I think I've mentioned the word machine learning too many times right now without actually explaining what it is. So what on earth is machine learning? Machine learning is an umbrella term that refers to code or software, which rather than being procedural execution of rules based on inputs to obtain outputs, is actually iterating over inputs and outputs to figure out the rules. And these rules, once found, are saved, and this is what we will refer to as a train model or a deployable model. So this relationship between input and output, which is the red line that you see on the figure, is nothing else but an equation, usually a complex one, if you compare it to Giro's lobby equation. But that equation follows what we call the bias variance paradox. So if the equation is too specific, we overfit, which means it will fail to generalize, or if the equation is too generic, we underfit, which means it will fail to give us useful predictions. So what we're looking for really when we're using machine learning is a good enough fit, a good balance between bias and variance, which would work on most generalized book cases. So there's a whole ecology of these types of equations, which we will refer to them as models. Some of these are really old, some of them are more new, some are old ideas empowered by new hardware. We won't go into the technical details during this talk, but I will be mostly showing examples of deep learning. So maybe I'll take a minute to explain what it is. So deep learning, or basically neural nets, if we generalize, it's a concept that dates back to the mid-80s, actually. And it's based on the neuron as a building block, which you can see here on the slide. So it's nothing else that an input that is passed, and then there is some algebraic math that happens, and that gives us an output. And the power of the neuron is actually not in the ability to use one, but to stack them in different ways, creating different model architectures, so to create more or less different complex functions that would be used for different purposes, basically. So this is point number 2, which is the model. And then point number 3 is what actually is the value proposition that machine learning brings to architecture. And to maybe start talking about this, I would like to show this graph that I like a lot by Stanley Smith, which I quote is the curve depicting the beginning, growth, and maturity of anything, whatever, because I feel it is particularly relevant for machine learning as a technology. However, I feel that the curve, the same curve for the same technology, is very different in different fields and industries. So it can be really ripe in computer science, for example, but not so much in bioinformatics or in computational design and architecture, for example. So this review paper, which was written by Mateusz Wiericki, we can see that the appearance of the word machine learning and artificial intelligence in computational design papers is at the full upward swing of the slope. So we're still in the first part of the Stanley Smith curve, if we want to think about it that way. And a lot of researchers are actually looking to do all sorts of things with machine learning, trying to tease out the correct methods and workflows and see what this technology can actually be used for in our field. And we see this, we know, in computational design conferences, where since 2-3 years now, there is always a machine learning related paper session, at least one. Is this a déjà vu? One can't help but think of that. And have we seen this before when architects appropriated the robot arm and moved it from the assembly line to the lab and started doing all sorts of things with robots, things that are very varied and highly bespoke, but also very precise, which we could not think of doing in another way, or not using a robot arm. And the reason why we are able to see this proliferation is because we managed to migrate from this way of programming a robot, which is using highly specialized manufacturer-specific software where you have to click, 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 and and write line by line of code to produce a very small, repeatable task, which is what robot arms are actually designed to do in a factory, and actually move on to a more integrated approach to programming for robots using directly within our design environment, where we can totally link our design to so design and fabrication file kind of become one. So right here, we're using a lot of some of the open source tools that are available, such as Robots, which is developed by the Bartlett, but other tools such as HAL by Thibaut Schwartz, or even José Luis's Machina do sort of the same thing, right? Where rather than sitting there and actually writing every single line of code over a very long geometric toolpath, you just generate all the code and just push it to the robot. So this open sourceness, this accessibility and ease of use is kind of empowering architects to actually use these tools for non-industrial arm purposes and actually explore. And I feel that there's kind of the same dynamic which is happening right now around machine learning tools, where they're kind of the entry barrier is a little bit lowered. So libraries, which are, state of the art in a lot of industries, such as TensorFlow and scikit-learn, are extremely well documented on the web, but also there is some direct implementations of some more simple, obviously, machine learning models directly in Grasshopper, such as Lunchbox ML or OWL, but also just using something like the hops component to directly connect to a Python server and run a machine learning model there. So it allows us to skip a lot of the interoperability barriers that would, stop architects from actually using these tools and getting down to actually using them. So what are we using them for? The first and maybe obvious, but not so easy to detangle potential of machine learning in architecture is design processes as a design aid. So, using pixels and graphs, you could interpolate design possibilities in high-dimensional design spaces. And these three examples are by no way exhaustive of what's going on in the community right now, but it's just a sneak peek of what's going on. And in the end, I feel this end of the machine learning adoption is actually very akin to the generative design field in general. But I won't be talking so much about this, because what I would rather us spend time to talk about is what interests me and my colleagues at CITA, and it's the ability of machine learning to break the serial relationship between design, analysis, and fabrication, which anyone who's ever designed something which had to be built had to swap between fabrication files and analysis files and move a point by 2 millimeters and have to rewait for the whole structural simulation to compute for 5 minutes and get stalled and so on. So how can we actually have a more seamless interaction between these three stages of architectural production? So by shortcutting design and analysis, neural nets offer the potential for iterative and interactive analysis-driven design, where the designer can skip, for a given simulation, the modeling and setup steps, and also modifying and recomputing comes at no extra cost because it's very fast. But also by shortcutting design and fabrication, we can unlock possibilities for adaptive and interactive complex fabrication processes, because maybe so much of the parameters that govern these processes are embedded within the intelligence of the model that you train itself. So the model encompasses everything, and you don't need extra bits of information, which are often the ones that are most difficult to set up and to provide and to juggle between. So if we go back to our machine learning checklist, we've looked at the what, which is data. We've looked at the how, which is the model, and we looked at the why, which is the target or the field of application, which makes it sound very, very easy, but it's not. And remember that little asterisk on data? Well, I lied a little earlier, or reduced the complexity of the topic. It's actually a data set and not just data. And the difference between data and data set is that data sets are organized sets of data in which you can control both the distribution as well as the encoding of your data, or the representation of the data. And these two aspects are actually really important to the quality of your data set. And always remember that the better your data set is going to be, the better your machine learning algorithm is going to be able to learn and generalize afterwards. So it's really important to control these two aspects. So the problem of distribution, this one is a bit more straightforward. It can be handled using statistical methods. So if you're using existing or harvested data, then you can solve imbalance using over or undersampling. If you're generating your data directly from a design environment, methods like data visualization, bootstrapping, k-means clustering can be used. And so that you can control which areas of your high-dimensional data space you're actually sampling from, and what that would do to the quality of the prediction, both for in-sample but also out-of-distribution queries. And this is something I'm currently looking at in my PhD, which is how do you actually set up a design space that would then give you a valid data set, essentially. And then the second problem, which is the problem of representation, and this one is not such an easy thing to figure out. It's also not a new problem. John Giro has written about this 30 years ago in a paper called 10 Problems for AI in Design, and problem number 1 being representation in design, followed by design semantics, coding and decoding, and inference in design. And to try and explain this a little bit better, let's look at this very famous in computer vision case of Lincoln's black and white portrait. And the initial layer of the representation and encoding problem has to do with the fact that neural networks are highly parameterized function approximators. So they need to work on numbers. So there's an exercise in reconciling every other format into a number. In this case, just using the pixel value on a grayscale. But the second layer is actually having to do with the choice of parameters of representation. So for the same given data, the way you represent it kind of makes or breaks your model. So in this case, it's a very simplistic example of the same set of points, whether you represent them as Cartesian coordinates or as polar coordinates, makes a hell of a difference in making them linearly separable, which makes it easier for the algorithm to actually be able to classify these points, the blue and the green groups separately. So there's a lot of tinkering about what are the right parameters. There's some statistical methods to figure that out using PCA and so on. But really, when you're doing machine learning, it very much often boils down to problem representation. And you can get as creative around this as you want. Granted, it works, obviously. But what I'm going to try to show are ways to produce valid problem representations for architectural problems to be used so that you can use machine learning to solve these problems. So you can see that what might work for Lincoln's portrait doesn't really work with a picture of the Sydney Opera House, for example. So for architecture and for fabrication, choosing the right data encoding becomes extremely difficult because on the one hand, our data comes in a variety of formats, and it's kind of easy for us to choose which format we want. Do we want a NURB or a mesh? Do we want an image array, or do you want a list? Or what is it? How can we format our data? So there's a lot of flexibility in this, but at this other end, there is reconciling it with existing input formats that these neural networks can accept, because we need to translate our geometries, our spatial qualities, our fabrication parameters into something that is machine learnable without losing any of the information or any of the data. And the meta problem over here is actually that we are using tools that were never built for architectural application in the first place. And we're trying to hack into them, a bit like we did with the robot arm, and try to use them for something useful. So these tools were built to, recognize handwritten digits and, facial expressions, a cat or a dog, and all of a sudden we asked them to design a floor plan for us or something of the sort. And even the data sets and the models that work with 3D data, which one would think is what architects would be working with, are very generic and don't necessarily straightforwardly lead to a architectural application. So it's really a lower problem of making it work for your own data, but also a higher problem of how do we actually get the industry to develop relevant models for our applications, which they're starting a little bit with the whole geometric deep learning by Michael Bronstein at UCL. But the reason why that started is because of social media, not because they were in love with meshes. So there's also a lot of hidden meta level and meta forces that we don't control. But what we can do is try to, bridge the gap and try to find a way to make these two pieces that shouldn't fit together of some sort. And how do we do this? Well, there's another pearl of wisdom from the 90s that I like a lot by Wolpert and Macready, which is there's the theorem of no free lunch. So you can only know something by trial and error, and trial and error, and trial and error, and a lot of patience. So we're left with no other choice if we want to use machine learning for architecture than to actually create our own data sets. And frankly, if you ask any scientist, a data scientist working on machine learning problem, they will tell you that over 75% of their time is used dealing with the data, really. So, we're not that different. So custom data sets, where can they come from? They can come from web scrape data. That's very useful if you're working with a lot of urbanism and OpenStreetMaps and so on. There's a lot of open source data there. But it can also come with from either physically prototyped data or digitally generated data, which is most likely what you would need to use if your problem is extremely specific or if you cannot use data that is available on the web. And this is mostly the data that I'll be showcasing with the projects today. And then regardless of where your data comes from, you need to encode it or you need to represent it, which is what we talked about before. So there's different ways. One way is just basic numerical encoding, where you create a string of parameter states. And this is very easy when you're actually creating your data from a digital model, and it works well with deep neural nets. The other way would be to work with data with convolutional models. So these models are very sensitive to where things are with respect to each other. And for that, you would use ND arrays. So there's like a 2D of some sort, and you could represent a variety of things. They don't need to be visual images, but in this case, for example, it's the print toolpath of the tile that you see on the right. And the extension of this is to think of these arrays as actual images. So here, I don't mean figurative images, but rather encoded images, where you can encode different properties into the red, green, and blue channels of an image and create these false color images, which to the human don't mean anything, but actually to the neural network carry a lot of information. And this information can blend geometry, performance, and so on. It's up to you. And these also lend themselves well with GANs and with convolutional autoencoders. And the last type of encoding, which is also something that is very much ongoing work for me, is working with graphs, and that would kind of pair well with geometric deep learning, which is graph convolutional networks. And here, what's interesting is that you can stack different graphs onto each other across time, but then what becomes really important is kind of the topological relationship between your data points. So this is when I stop bombarding you with theories and a lot of abstract notions, and maybe start showing you some of my projects that we've been working on and that apply machine learning to architectural fabrication. So not with the aim to provide any answers, but more to exemplify some of the approaches that we've used before. So I've made this little map of the projects I'm going to show you, where on the x-axis, they go from analysis to fabrication, which are the two targets or intents that we work with. And on the y-axis, they go from digital data set to physical data set. Makes sense to start with this project, which is the precursor to a lot of the machine learning work that we do at CITA, the Bridge Too Far from 2016, and learning material behavior, in this case, metal sheets. I didn't personally work on this project. It was developed by Paul Nicholas and Mateusz Wilicki while I was doing my master's at KADK, but it has very much influenced my thinking and some of the other projects that I will show in a minute. So, using numerical encoding and physical data set, why should we predict material behavior? Or how can we predict material behavior as well? So CITA had been working with dual robotic incremental sheet forming for a couple of projects. And while rigidizations are actually great for structural performance and resisting bending stiffness, metal actually springs back while you're forming it, which means that the geometries you intend to fabricate may not be what you end up with due to the spring back. So can you actually use machine learning to predict it? Yes. well, there was a vague idea about which parameters were informing the string back. So the depth of the features, the proximity to the frame and to the previous features, and the irregularities present in the metal sheet from the manufacturer. So overall, it is a difficult combination to rationalize, but if you scan all the pieces and then you are used as a data set, you train a deep neural network, and then you get a model that is, if deployed in Rhino, is able to actually compensate for the spring back. So they validated the trained model by comparing the predicted meshes versus the actually fabricated geometry and comparing that with the input meshes that were present in the digital model. And also, once that was confirmed that it actually worked, then use the reverse prediction mechanism, which is to say, if I want this to be my end target, what should I form? So actually working on the digital input mesh that sends the instructions to the robot and how actually overcompensated it should be. And they built this amazing bridge, which is only 0.5 millimeter thin aluminum sheets. I don't know how much in inches that is, but it's very, very thin. And it can stand people crossing the bridge, which is the purpose of a bridge. So that brings us to the second project that I want to talk about, which is actually my master's thesis back in 2018. And it's also metal, it's also a physical data set, but given the nature of the forming, the assumption that out-of-plane incremental sheet forming could be represented numerically with a Z displacement value was had to be rethought due to the English wheel process, and hence why we started using the image encoding here. So to those of you who are unfamiliar with the English wheel, it's a device that turns a flat sheet of metal into a doubly curved sheet of metal. So it's very smart because it's waste-free. It's a waste-free way of making strong shaped pieces, but it's also a craft and it takes years to master. So how would you actually program a robot to do it? It's much more complicated to do that than to just program a simple milling toolpath or hot wire cutting or so on. So can actually a robot learn a little bit of a more complicated craft to perform? So the idea is to implement a cyber-physical system with a scanner and an advanced computational model and create a feedback loop during and after the fabrication. And for every piece that is made, it's then archived and becomes part of a larger data set or knowledge base. So, the more we use this process, the better and the more accurate it's actually going to become because it can train on more data. And so again, we made some samples and try to understand what is actually the design, the extent of the design space or the parameter space that we are dealing with, and what geometrical implication do different parameters entail, so that we can actually compose a data set that is, well distributed. And so there was some robotic programming that was done in Grasshopper. Where you start off with a flat sheet of metal, and then as you form the first pass, you need to scan it. That scan is registered and it's reconstructed and then is used as a start for the second pass and so on. And then our data encoding, this was the first time where we used false color imaging, and this was actually the version that best worked. And from there, we just trained a convolutional autoencoder on Keras because it was 2018, and this was as far as convolutional autoencoders had gone. So you can see on the left the tracking pattern encoding, on the right the geometry encoding using some false color XYZ coordinate positioning. And we made lots and lots of samples. So you can see here, this is real time. So it's actually pretty fast to make a sheet. There were some size limitations due to the workshop setup that we have, but overall it takes less than 10 minutes to machine a piece. You can flip, you can machine backwards, you can produce all sorts of curvatures. And I, frankly, got quite obsessed with this choreography that the robot was doing, producing all these nice shapes. And what was nice to see was also the physical expression that these panels have, that they're very different from what a handmade English wheeled piece of metal looks like. Really the marks of the robotic arm are very different from the marks of the human. So it's not really about, you know, replacing the craft, but it's more about augmenting the craft and extending the craft and seeing what the robot can actually bring to the table. Following from that, the project I want to talk about is also on the fabrication side, but in the digital quadrant. So it's actually a project done by two of my students, Cami Quinteros and Hisham Shawi, which I had the pleasure to teach last spring during the machine learning and data encoding course as part of the MACAD master program at the IAC, the Institute of Advanced Architecture of Catalonia. And it takes on the similar aim as the English Wheel project, modeling a craft through neural nets and being able to deploy it with digital fabrication. But this time it was clay throwing, not the English Wheel. And the data set was entirely digital and numerically encoded. So the students cleverly designed a parametric model which created these vessels based on interacting forces. And well, this is a great script, but the limitation of it is that it is iterative and time step based. So it's not very practical if you need to quickly send instructions to the robot, but it's very practical to create thousands of samples, which you can then train a neural network to do the relationship between the robotic parameters and the geometry parameters. And they were able to train two neural networks, one that predicts fabrication parameters from geometry, the other that predicts geometry from fabrication parameters. And it's really ready to be tested on a real robotic station to actually test this clay throwing process. So it's all very exciting. I won't tell longer about this project because they are actually presenting it next Thursday at Acadia. So do tune in to listen to the full explanation from the wolf's mouth, as we say. Next project, which also utilizes a digital data set, and if you remember from the mapping, and it's not really fabrication, it's not really analysis. To be very frank, the whole idea started as a provocation where we were bothered by the absence of proper clash detection in our robotic programming environment. So on a meta level, we were asking whether a neural network could replace a kinematic solver. And so whether we could learn path planning rather than, you know, detect clashes and program against them, which is usually a manual process. So again, we use numerical encoding, and the idea was to use an obstacle avoidance routine that could be grafted into a predefined path, and then, you know, see where that could go. So it's very explorative. This was our data set. Basically, the robot reach was populated with some trajectories and some obstacles. And here you can see the robot learning how to move like a baby. Basically, we created, just by encoding a target sequence and the resulting axis angles of the robot along this path, you could then teach it to move. So you can see it here following the line. The blue one is the one that is traditionally Cartesianly programmed, and the white one is the one that it comes from the neural network. You can see it also go over an obstacle in different configuration and orientations. And what was really fascinating was its ability to generalize to curves that it hadn't really trained on. So I wouldn't recommend this for dangerous tasks. Like if there's a spindle involved, please do actually look at clash detection as a human. But this is really good for like pick and place, and was really a lot of fun to work on this. And the idea is that once it's trained, you can then tune this digital data set to the actual end effector that is being held. So whether it's actually the safe spacing on each, or if there's a safe configuration that you would prefer the robot to go through. And this is really nice with cobots because you can just, you know, freeze the wheels and you could then quickly tune it to what you wanted. And the last project I want to show you today, and then I promise I'll stop, is this one that is situated in the digital analysis quadrant of the map. And it uses an image encoding and a digital circuit dataset. So we developed this year during a workshop Paul and I ran at the University of Technology of Sydney with some of our colleagues down there. And it was right before the pandemic. So yeah. And the context of this is that conformal 3D printing, basically. And the idea is that these are some found panels which are scanned, and you could 3D print a reinforcement, structural reinforcement to it on the sheets. So how do we actually run a structural analysis on a point cloud, because that would be so much faster than having to take a point cloud, mesh it, set up a structural simulation, get the results, and then generate a pattern, right? So could we short circuit that part of the workflow? And I guess the answer to how is, well, you know by now, machine learning. So we created a digital data set of a few thousand samples. The inputs consisted of a geometry with a load case, and the output was a finite element analysis result, namely the von Mises stress and the deflection. And if you hope this diagram is still familiar to you, so what we did was actually to use this false color imaging approach that we've been testing, where we also actually just used two of the channels. The green channel was inactivated, but you could mix together multi-dimensional, multi-source data. So in this case, we both expressed geometry and performance through the same image. So a lot of these, we train CGAN this time because it's 2020, and then the network turned out actually pretty good. So just to the naked eye, I cannot see much difference between the prediction and the truth, but we've also validated it against an actual structure analysis of the piece, pixel by pixel difference, and seeing how off were we on the stresses, and it wasn't bad. So this then became our accelerated, structurally informed, on-the-fly robotic conformal 3D printing workflow. So you scan your piece. The point cloud is processed and encoded. It's queried. It's sent to the trained deployed network. You get a prediction, and then that prediction drives a generative toolpath then in Grasshopper. And the toolpathing was something that we developed with our students. So it's just a generative branching algorithm in this case that just takes the predicted bitmap as a field for the values. So. And so you could see here the sensing robot, which has two scanners, a depth sensor, an Intel camera, and a photogrammetric RTEC scanner. You get a point cloud on the fly, and then you then do all the processing in the background on Python, and then you can get a toolpath that you then send to the other robot and is printed. So, to wrap up, I guess my 5 cents are that machine learning tools are very powerful. They go beyond current modeling paradigms in a lot of ways. Dataset composition and data encoding are really crucial to the success of the model, or will cause the inevitable failure of the model. Digital augmentation to physical data sets or digital surrogate proxies to physical data sets are really what makes it viable in the case of fabrication, because it's highly unlikely you will be there to design and produce 2,000 pieces. So either there's a smart way of augmenting the piece, or you need to be sure that that piece is the right piece in the distribution, or you just need to do it digitally. And creating machine learning workflows is time and effort consuming. So if there is no real reason to deploy it using a machine learning, like if doing it via machine learning doesn't really add anything to the process, then you should not do it with machine learning. And yeah, just stay curious, stay critical and ethical. And thanks a lot for listening. And all of the projects I've talked about are actually published papers, so you can read more about the details using the QR code, and feel free to reach out if you have any questions. That was my last slide. So.
All right, thank you so much. Can we all give Gabriella virtual applause, digital applause, in whatever form in this crazy Zoom world? Thank you very much, Gabriella. That was amazing.
Sure. Sorry, I ran a bit over time, but
oh no, we're very good on time. Don't worry. Just a quick reminder that I'm going to open this up to Q&A to the people on this call on Zoom, and also to those on the chat on the YouTube live stream. So if you want to start typing your questions, or I will give it up very soon. So perhaps to break the ice, Gabriella, this was amazing. Thank you very much. This was the best 2-minute crash course on machine learning that I've seen in my life.
That's very good to hear.
And I've seen some, and I was particularly moved when you referenced Stanley Smith. I love him. I've been reading a lot about him, and I keep being constantly moved and surprised by his sensibility to history and to the nature of civilization and culture for someone who was so into the technicalities of materials and metallurgy. And I think he was actually involved in the Manhattan Project as well, wasn't he? And
not sure, but
I believe so. But anyway, like I totally like destroyed him in my dissertation. By destroying, I mean like I read the whole thing, and it was amazing. And I was also very happy to see that you mentioned how some of your work ended up, some of the work from your student ended up in Acadia, which is going to be presented next weekend. This is just a friendly reminder to those students in this call, because we are not going to have class next Thursday, because I asked them to register for free to Acadia. Reminder, Acadia is free for students this year. I asked them to register to Acadia next week, and to, instead of coming to class, attend one of the panels, the one that they're most interested in, and then just write a small report over that. So if any of you were interested, or you want to join the panel where Gabriella's students are presenting the work that she just showed. So I was personally very interested in how you showed a very strong digital approach to generating data sets for actual fabrication, which is one of the things that I dread personally about doing machine learning for fabrication. The fact that if you want to generate a data set, which most of the times you have to, because there's nothing, and especially for fabrication, there's nothing out there that you can download.
Yeah.
Generating the data set is just such a consuming and tedious process when it comes to physical experimentation, you know, and I could totally hear you saying like, oh, the English wheel is so fast, you know, we could generate data sets very fast, you know.
It's not what I was saying, but I think there's a lot of, there's two ways to think about it. Either you go the one-shot learning way, which is very few samples that are very relevant and covering your design space, and then you can get a decent prediction out of it. Or you sort of do a hybrid between, you know, physically producing a piece and then digitally augmenting it. So you can do mirroring, you can crop, you can do, there's a little bit of hacks that you can do, but obviously you need to make the thing, right? Or you can trust a digital surrogate, and then the question becomes, okay, so to what extent is the digital surrogate okay, and to what extent will then you would need to tune maybe your learning algorithm afterwards with 10, 20 fabricated pieces, right? So which
sounds to me like a fantastic research of meta research, like a fantastic line of meta research. Let's figure out simulation frameworks that are able to simulate fabrication reality so that we can generate synthetic data sets for fabrication. My mind just exploded right now. I know, but perhaps the question that I wanted to direct more your way is like taking a couple steps back. I was very happy when you mentioned that machine learning is supposed to be a technique that is able to generate generalizable knowledge. You were talking about overfitting, underfitting, and coming up with a balance of something that is able to predict with a reasonable degree of tolerance something from a framework, right?
Yeah.
Now, I keep constantly engaging in conversations where the role of machine learning architecture is questioned completely, and mostly from parties that believe that the architect as a creator cannot be replaced and shall not be replaced because of the human touch, etc., which basically relates to the idea that in the creative fields, the concept of generalizable knowledge, it's a little tricky because we often pride ourselves with being creatives, so people that can come up with new things, not based on experience, like machine learning models do, but based on intuition, spontaneity, serendipity, those kind of things. So what does the role, for perhaps in a more philosophical way, what does the role of generalizable knowledge, like the one exhibited by neural networks. What role do you think it can play in creative fields, and how should we frame that?
Okay, I think there's two parts to my answer. The first one is that when we talk about generalizable AI, whenever anyone talks about AI, they're like, "Oh, AI is gonna compete with the human brain," and that's kind of maybe the strong AI side of things, which is not really what I'm trying to do. At least I'm trying to get a really good predictive model that is very good at a sort of specific task, has its bounds, has its limits, because there's kind of the inherent problem of the parametric model. Model will never be able to get that one singularity. Maybe it's an error, but it will never be able to show you that one design or that one data point that is not encompassed in its dimensionality, right? So it's kind of the same problem, because when you're training a data set, when you're training a model, all it knows is your data set. It might be able to interpolate to sort of out of distribution. So we were playing a little bit with the load cases in the last project I showed, and whether if we put a different load case, would it be still able to generate a stress pattern that was real? And sometimes it was yes, sometimes it was no. And the times where it was yes, it was because it was sort of similar to something else it had seen. So in setting when I said that it's when you're working with machine learning, it's a problem representation, but it's also a problem setting exercise. So to what extent do I want it to be good at predicting? Because it cannot predict everything and anything, then you would need, huge amounts of very varied data. So you can't really, I think AI is not a general tool. Machine learning and AI are very specialized tools that are very good at predicting a generalizable version of a specific problem. I don't know if that kind of tackles the first part. Then the second part was about creativity and our design instinct and so on. It's a little bit what we're trying to do with those craft exercises. Is like there's so much embodied knowledge in the craftsman who can feel whether I need a little bit more here, a little bit more there, and maybe it's not about replacing that craft. It's about empowering it, or actually being an add-on where you can do 90% with the robot very fast, and then the last finishing touches are what you put on if you're making a custom bespoke classic car, for example. Then you will always need a hand, because the value of it is because it's artisanal, right? So we're not competing with artisans. We're trying to find synergies and ways to make things more productive and better. And I think that the conversation about whether our AI will take over the world, or architects and are superior because they have creativity, or so on. It's a bit like the reaction people had when generative design came out, and genetic algorithms and Galapagos and optimization results and so on, where the creativity is not lost. It's just in a different way. When I design this encoded image, false color image system, it's a creative process for me, because I'm thinking, how do I find that solution to that problem? So maybe it's not in the design, but it's in the process. And designing processes is just as part of our job as actually, I think, designing buildings. Designing processes, designing software for our processes, designing interfaces between these softwares. I think, it's really reductive to think of architects as just, we do buildings. We do more than that, much more than that. We design society in a way. So it's, I don't know.
Okay. Has everyone heard that? Architects can do much more than design buildings. I'm kind of a recovering architect myself, so that's why I'm a little like, we can do other things, and it's great. We can actually, we can do that. Thank you, Gabriella. And before I open it up to questions, I get questions all the time on social media, on my courses, etc. Of like architects and designers who are interested in harnessing the power of machine learning, but they don't really know where to start. They're completely new to the field. What would you recommend someone who just wants to dip their feet in machine learning and comes from a creative field? What do you recommend they do to start?
I think, read papers, but also just get your hands dirty, because you can read a lot and it will sound so interesting, and then you are there in front of a blank screen and you're like, how the hell did they do this? And I have no skills to implement this, or so on. So try to, read a little bit, but then also there's a lot of platforms that make it so easy to do AI. So there's what's it called, runaway ML, which is really makes GANs really easy, really. And but also like all those Grasshopper plugins I've been showing, so Lunchbox ML and all, they're basically neural nets without you having to code. You just put in data trees, and I assume data trees is something that is a bit more accessible than, you know, Python libraries.
Beautiful. Thank you very much, Gabriella. I'm
Sure.
going to open it up to questions. I see on the chat here on Zoom that I see that Austin Liu had a pretty... Austin, would you like to unmute yourself and ask the question right away, or should I just relay it for you?
Sure. I mean, I can ask the question. So just because I know that recently, so there's with the disruptive supply chain and also the labor market, so there's a change during the pandemic. So it seems like 3D printing housing could be a practical application, and I noticed that there are a few more startups that coming up in the market, and so there's a growing need in the construction industry in the future. So I'm just kind of curious. So do you think 3D printing housing could be a good opportunity, maybe just for students or just for an architect in the future? And how do you see the application of machine learning in this kind of mass construction or fabrication of 3D printing housing in the near future? I hope that's clear.
Sort of.
Thank you.
Yeah, thanks for your question, Austin. So part of the stuff I didn't show today is actually what I'm working on for my PhD. And what I'm working on is coming up with a predictive model to be able to use biopolymers as a 3D printable material. And the reason for that is because the way these biopolymers behave when they're 3D printed and when they dry is very different than other materials when they're 3D printed. So it makes it, you know, it's a kind of entry barrier to how we could use them. So if we can model them, then maybe it's a good way to start using them, and it's a very sustainable material, which is very good. There is a lot of research that goes into modeling concrete when it's being 3D printed, because, you know, it's in this viscous equilibrium state and there's a lot of structures involved. So maybe machine learning models could also be there. I'm personally not that much a believer that we should all 3D print houses, because it kind of sounds a bit like we should all build prefab, which happened 60 years ago and turned out to be a mess. So I think we should really rethink our materials and which materials we use and how much of it and what's their life cycle and what's their impact and so on. Because I feel if we don't change that now and embrace a bit more of a sustainable choices in the most basic need that we need, which is a house, then I think we'll kind of never get there, generally speaking. So yeah, so I think also I made it clear with my presentation that my interest is not so much in AI for design, but it's more as AI for predictive models that are very specific to something. So if material behavior in 3D printing is one of them, then I see that as an application.
Okay, thank you.
Yeah.
Beautiful. Mira, may I invite you to unmute yourself and ask?
Yeah. Hi. Hi, Gabriella. Thank you for the presentation. Those are super fascinating projects, especially the ones that's point cloud structure analysis. I was wondering, with all your projects, was there kind of figure out what type of machine learning algorithm that you're going to use, or did you already know that you're always going to use GAN or CGAN?
Yeah, so the choice of which algorithm to use with which data type is kind of given by the nature of the algorithm. So CGANs use images, and we found that they're very useful if well, you can read this on convolutional networks, that in general they're very good at understanding the spatial relations between parts of your data, basically between the pixels. So pixels that are neighboring to each other will kind of inform each other in the learning process. So there's a lot of math there, but that's not the point. And so I think the answer to your question is, depending on how I can encode my data in what format, whether it's an image or a string or a graph, then that's what sort of guides the choice of model that we use. And there sometimes it's the backwards. So one limitation with the bridge too far was the fact that it used deep networks. So the next thing to try was to actually see whether a convolutional network did it better. And so the need to shift your representation. So it kind of goes both ways. And when I'm working with new things, I kind of test different representations and different models that go with them. So you cannot, for example, use, I don't know, a graph GCNN with an image. It just doesn't work. You need a graph as an input. So does that answer your question?
Yeah, thank you.
Yeah.
Awesome. I think at this point, I'm going to open it up to questions from the general audience, also including our YouTube viewers. Yeah. And just in case you haven't checked, Gabriella, but there's a lot of love coming your way from comments in the chat. So I encourage you to check it out afterwards if you don't have it on a side monitor or whatever.
No, I don't. Yeah, focusing.
yeah, of course. And yeah. There's also a lot of people from the community and people that I actually know. It's great to see you. So I'm going to relay a question from Abhishek Shinde, who I actually believe is also based in Denmark these days.
Yeah,
right?
I know him. Yeah.
You know him there.
We know each other, yeah.
I know, I assume. Yeah. So he's asking how can structural behavior can be used as parameters for false color imaging as data sets? I guess the question is about how did you encode structural behavior in those false color images that you were showing today? What was the mapping?
Yeah, so what we did in the input was to define where the support points were. Those were the red dots in my images. And then in the output, we had one channel represent one structural result. So the red channel was representing the von Mises stress, and they were remapped. So the maximum and minimum were remapped to 0 to 255, which is how we use a RGB image. And the blue one was the deflection values. So this is the thing. So when you're actually trying to create these false color images, what you need to think about is what is your range of your variable, and then how do you remap that to 0 to 255, which is what a pixel can carry.
Mm-hmm. Did you hear that, folks? Normalization.
Yes,
I've been talking
very
about
important.
This. I've been talking about this like forever, every single class. Let's unitize our vectors. Let's normalize our ranges.
It's very important because then you can actually read what your data is, because otherwise you're dealing with ranges and you have outliers, which you need to, take out. Otherwise you get a statistical mess. Yeah, anyways.
Good. Very happy to hear that.
Yeah.
Ananya Kango is asking, in the case of examples where the machine learning model is used to predict the toolpaths, how do you imagine it changes the whole design to digital fabrication cycle?
Well, I don't think it changes that much. It's rather than using, the create program component in your Grasshopper plugin, you're using the get me the prediction. Obviously, in the level of work I have done until now, there's always been some post-processing that needs to happen where you get the prediction and then you have a moment where you look at it as a human and you're sure this is safe, and then you get the code out. But I believe that if it's robust enough, you could just, get whatever input generates the code directly from the machine learning algorithm. So it doesn't really change that much, just changes what component you're using. So
a question from Kevin Moreno, also a friend. Do you think these ML workflows would do robotic fabrication more independently from the digital world? Like, in other words, based on more analog tools or helping people without technical knowledge?
Well, could be. So we had some projects where I worked on at CITA where we had industrial collaborators and actually people in the shop that we had to create tools for. Also at Odico, that was something that we did a lot. So we created these interfaces where it was on the front end, it was a very simple interface, but then on the back end, there was a lot of computational juggling around that was happening. And as long as the way it presents is very simple and accessible, and the back end being robust enough to not throw errors every 2 seconds, I think it could be a way to actually, open up these tools to a less technically skilled demographic. I think it's part of the making things more accessible. The same way that Grasshopper plugins make algorithm implementation accessible to to computational design coders. If we create front ends that are very accessible and intuitive, then you can also open up these complex algorithms to more people that could use them.
Awesome. And perhaps the last question for today, and then we just we let you go. It's a little late in Denmark now.
That's fine.
Matthew Tanti is asking, do you believe that AI can predict the way we use buildings through time? And if so, do you think it can be used for architects to use these technologies as a way of pushing for new legislations? Sorry.
Okay. When you say, I don't know if you replied in the chat, but when you say how we use buildings, is it the users or is it the material that is getting old and used? So if it is users, there's actually a colleague of mine, Jens Jorgensen, who's working on this at CITA. So he's using machine learning for occupancy evaluation of buildings. So he's using machine learning to generate, semantics out of people being in rooms and interacting with things, and from there also trying to translate that into information that can be given to the design team in an office, and so on. If it is about materials aging and the building getting some wear and tear, then yes, I believe you could do predictive models of weathering. Right now, what people use is either real-time monitoring over a couple of years or QUV chambers, which are accelerated weathering cycles. And there's currently no way to actually map the two to each other, I was very surprised to find out. So maybe one way could be to have like a translator from one to the other, or also just model things using machine learning. So.
All right. And before we end, I also want to relay, because it's not questions, but there's a lot of beautiful comments such as, this lecture was awesome, this is so cool, enhance emoji, ovation, great work, thank you for the amazing presentation, very inspiring work.
Well,
100 emoji.
Yeah, I'm glad people didn't find what I said boring, but that's great.
All of which are feelings that I also that also resonate with me. Thank you very much, Gabriella. It was a pleasure to have you with us.
And thank you for having me. And just get in touch. Feel free to get in touch if anyone.
Where can people find you if they wanted to reach out? You had a last slide with
a few
so handles.
I will just. Do I just type in my email? Is that a good way?
Or you can just say it, because YouTube people will not be able to get it.
So it's garo@kglacademy.dk, which is very bad.
I'm gonna copy it on the YouTube channel.
Yes. Yeah. So you can just Google me and probably find me. Yeah.
All right.
But thank you so much.
Thank you very much, Gabriella.
Nice,
thanks everyone. Pleasure. Can we give her a round of applause, virtual and digital, however that is. Thank you very much, and have a good night.
Yeah. Have a good evening. See you.
Bye-bye.
Bye.